Tap play and one video frame runs a gauntlet. Radio waves, glass fiber, raw silicon, all to reach your eyes in about 20 milliseconds. 4 handoffs. Miss one and it arrives late. Here's the whole chain. Why does 20 milliseconds matter? That's the line between video that feels alive and video that stutters and buffers. Your eyes notice the lag long before you can name it. And here's the catch. That tiny time budget gets spent across 4 separate handoffs. Blow any single one and the frame shows up late. So forget abstract data. We're following one frame the whole way. Hop 1. The air. Your phone can't send a picture as a picture. It converts that frame into radio waves and flings them at the nearest tower antenna. So which radio waves? 5G reaches for higher frequency bands than 4G ever used. Midband sits around 3.5 GHz. The extreme edge, called millimeter wave, runs near 28 GHz. Here's the trade. The higher you go, the more data you can pack into each second. But the shorter the distance, those waves survive before fading. Millimeter wave is blisteringly fast and barely crosses a street. Now one channel would be a bottleneck. So 5G doesn't use one. It slices the frame across hundreds of narrow radio lanes stacked side by side, each carrying a sliver, all transmitting at the same instant. That trick has a name. Orthogonal frequency division multiplexing, or OFDM. Think of it as 100 trucks leaving together instead of one truck making 100 trips. A huge amount of the frame lands at the tower inside a single millisecond. Quick gut check. This first hop covers the shortest distance in the whole journey, sometimes just a few hundred meters. Yet it does the heaviest lifting on raw speed, because squeezing a frame into thin air cleanly is the hardest physics in the chain. The frame is airborne, but radio waves are messy and full of noise. Something has to catch them and clean them up. Hop 2. The tower does its job. The antenna catches those noisy waves and hands them to radio hardware bolted right there on the mast. This gear digitizes the signal, turns wobbly analog waves into clean, exact bits, and scrubs out the interference. But catching your frame is only half the problem. A tower serves hundreds of phones at once. How does it avoid tangling them all together? The old way was to broadcast in every direction and hope. 5G does something sharper. The antenna isn't one antenna. It's a grid of dozens of tiny elements working as a team. By firing each element a fraction of a moment apart, they steer a focused beam that points directly at your phone, like a spotlight tracking one person in a crowd. That technique is massive MIMO, and the aiming part is beamforming. Because the tower aims a private beam at you and a separate private beam at your neighbor, the two frames never collide. One tower, many phones, no stepping on each other. That's the payoff. And it means power isn't wasted spraying signal at empty sky. It's concentrated on the devices that actually asked for data. Your frame is now clean digital bits, sitting at the base of the tower, aimed and ready. But it's still stuck at the edge of the network. To reach the wider internet, it needs a road out, and radio won't cut it for the next leg. Hop 3. The long hauls. The frame leaves the towers, but not by air. It drops into a fiber optic cable and travels as pulses of light toward the heart of the network. This leg, called the backhaul, is the longest physical stretch in the whole trip. It can run for many kilometers. So why doesn't the distance wreck the 20 millisecond budget? Because light in glass is absurdly fast. It moves at roughly 200,000 kilometers per second, about 2/3 the speed of light in a vacuum. At that pace, a frame can cross a whole city in a fraction of a millisecond. Here's the real question though. Why glass and not just more radio? Radio through the air is fragile. It fades, it bounces, weather bends it. Fiber is a sealed pipe. It carries an enormous, rock-steady flood of data over long distances without the noise and the fading that plague the air. For a leg this long, you want boring and reliable, not fast and flaky. Along the way, the frame doesn't fly straight to a single destination. It passes through routers and switches, traffic cops that read its address and shove it toward the right path to the open internet. Each one adds a whisper of delay. The frame has now left your neighborhood entirely, racing as light toward a data center. But something at the far end has to decide where it's actually going. Hop 4. The brain then homes. The frame arrives at the core, the packet processing heart of the network called the 5G core. This is where the network confirms it's really your phone, not an imposter, then decides exactly where the frame goes and forwards it on. Now a clever shortcut kicks in. If the video lived on some server across the ocean, the frame would blow the entire time budget just crossing the planet. So the content doesn't wait across the ocean. Popular videos are copied and parked on servers sitting close to your tower, a setup called edge computing backed by a caching network. Your frame often travels a few towns over, not a few continents. Here's the quiet hero of the whole trip. Silicon. At the far end, a chip fetches the frame. At your end, the modem and processor inside your phone catch those bits and decode them back into a picture. Encoding at one end, decoding at the other. both done in a sliver of a millisecond, because if the chips were slow, none of the radio and fiber speed would matter. The frame's bits get painted pixel by pixel onto your display. Think about what just happened. 4 completely different technologies, air-aimed beams, glass, and silicon, each handed the frame off perfectly in sequence faster than you could blink. And this all happened for a single frame. Your video is 30 of these every second. So add it all up. The air interface, the tower's beam, the fiber backhaul, the core, and the silicon at both ends. String those 4 together and you get the round trip. About 20 milliseconds. Here's what surprises most people. The radio hop, the part everyone pictures when they hear 5G, is not where most of the time goes. The bigger slices are distance and processing. Light covering kilometers of fiber, chips authenticating, servers deciding, silicon decoding. The antenna is fast. It's everything after it that fills the budget. Which means 5G fast was never one thing. It's 4 separate systems, 4 different kinds of engineering, each quietly hitting its own slice of those 20 milliseconds. Break any single one and the frame arrives late, and you feel it as a stutter. And that single frame we followed from the very first second. Radio to tower, tower to fiber, fiber to core, core to chip. It's the picture now sitting on your screen. Refreshed 30 times a second without you ever noticing the journey. 1 frame, 4 hubs, about 20 milliseconds, and now you can see every step. But here's the thread we didn't pull. What happens when 10,000 phones at a concert all demand frames at once? Why does your fast 5G suddenly crawl in a packed stadium? That's a fight over shared airtime, and it's a whole mechanism of its own.